Yeah, thank you, Alex, for that very nice talk, looking into some of the what might seem, at least on the outside, as wizardry of DeepSeek, and certainly some really interesting results coming out, and looking forward to what everyone does next. So we're going to have a look more into what you can do with these low precision data formats. First of all, we're going to go through what they actually are. It's not necessarily clear to everybody, depending on what you've been doing in your working and private life. So number formats, as Alex showed, shout out to Claude for making a really nice diagram earlier. This is great. Number formats, we're used to a lot of things. Integers are sort of the simpler one. You've just got a bunch of bits and everything is the biggest you can represent with, say, 16 bits as an integer is 2 to the 16 minus 1. So you go from 0 up to all the ones. When you get to floating point numbers, it's a little bit more fiddly. So take, for example, float 64. This is your double precision. This is what you might do scientific simulations, things where you're calculating meaningful numbers all the time. We'll get on to how that's a bit different in AI in a bit, because a lot of the numbers in terms of physical quantities aren't so meaningful. You can't necessarily imagine what they might be. It's a bit more of a sort of internal representation. So float 64, you've got a sign bit. That's just 1 or 0, depending on whether it's a negative or positive sign of the number. That bit's pretty simple. An exponent, that's a bunch of bits where that is, you're going to raise that to the power of 2. So you've got some 11-bit integer. 2 to the that gives you kind of the range, essentially. This is how big or small it is. And then multiplied by that, you've got the mantissa here, which is 52 remaining bits. And that typically in these sort of formats is represented as kind of all of that is divided between sort of 0 and 1 on a sliding sort of scale. And it's sort of 1 plus that weird representation. So a number between 1 and 2 multiplied by this 2 to the something and then given a sign. And then as you go down, it's the same kind of general philosophy, except we have fewer and fewer bits. And then we get some weird things. We get things like float 16, where we've got a sign, 5 exponent bits, and 10 mantissa. So relatively quite a bit of precision, not that much range. We then get B float 16. It's still 16 bits, but we just shift that divide. So instead, what we do with B float is we have the same exponent, so the same range as float 32. So you can, but what you've got in between that is far, far fewer mantissa bits. So think of it as a much coarser, kind of not so much a grid, because it's not uniform in width. It sort of gets more and more coarse as you get to bigger and bigger numbers. But you're saying, I want the same range. I don't want to lose how big a number I can represent, but I'm less worried about representing numbers between these two, for example. So kind of good enough is good enough. And then we get down to float 8, which is what people like DeepSeek have been doing a lot of work with, where all of a sudden you start to get really, really low precision now. Actually, there's another float 8, because there's not necessarily one agreed upon format when you get this low, where rather than having 4 and 3 bits, you get 5 and 2, so you've got more range, less precision, but then you've got hardly any precision at all. And actually what we're going to talk about now is going even lower than that. So this is really into kind of new stuff, particularly looking at float 6 and float 4. 6 is really weird. Computers don't like 6. They like powers of 2. So we'll get on to also how we can get benefits from 6 as we go through as well. So the main topic of this is usually under the umbrella of what we call quantization. So we're going through what this is, why do we need to quantize models, or what benefit can we get from it, and how can we do this without kind of losing all the performance in the sense of it does the job we want it to. So we might get performance in terms of it's twice as fast, uses less energy, but if it doesn't do the job, then it doesn't really matter. So first of all, what is quantization? Really, it's just doing this kind of coarsification of the numbers that we can represent to say, look, is far fewer bits making things far more coarse. These two numbers that in float 64 are quite different, in float 8 might come up as the same number. Might that be good enough? If so, then we can kind of quantize it that way, just essentially making things quite coarse in that terms of representation. So if you think of like an image, if you take an image with a fancy camera, it's probably 8 or 10 bits image. If you were to make that 3 or 4 bits, often you see, like if you get a really cheap TV and you try and watch Game of Thrones when it was streaming and it was a bit weird quality, you get the banding in the dark scenes because it hasn't got enough different colors it can represent. That's essentially quantization. It just in that case, it wasn't deliberate. It was just a streaming problem. And people watching it on cheap TVs didn't really see a very good picture. So we'll go into a bit more about this, and then we'll go into the why and the benefits we can get from all this sort of thing. So as I say, we're trying to reduce the amount of data we need to do the job we want to do. What this is really is reducing kind of the memory footprint. So how much memory do we need on our computer, be it an accelerated thing, or it might be a mobile phone, or a doorbell that's got some really tiny model that recognizes people, or a parcel that's been left on your doorstep, things like that. particularly in cases where you've got very limited resources, you want to reduce all this as much as possible. Use less memory, but also you're loading things that are smaller each time you want to do some maths on it, so you don't need the kind of bandwidth. So where we have super expensive GPUs, IPUs, things like that with huge amounts of memory bandwidth, we don't necessarily need to be using all of that. And one of the big things with that really is that we often find ourselves, our computer theoretically, as we say, can do this many flops. It can do this many mathematical operations per second, per core, per device, and you can scale it all up. That's assuming you can get the data quick enough. And depending on the calculations, sometimes you actually find yourself what we call memory bound. So you can't get the data to the right bit of the processor fast enough to be able to keep up. So that, along with other things like power and other bottlenecks, are why we find actually we don't always get the best out of the chips that we've got. So even in cases where we haven't got the newest hardware that can do maths in super low precision, because up until now that hasn't really been quite where things have been going. If you look at traditional kind of simulation kind of workloads, everyone uses 64-bit, so why would they bother with a computer that can do 8-bit? They don't really sort of need that. Even in that sort of case where your accelerator maybe can't do the maths in 8-bit or 6-bit or 4-bit, you might find that you're still doing the 16-bit stuff faster if you can get the data loaded a bit more quickly, or you just don't need as much memory, things like that. So there are a few ways we can do this. So if we want to what we call quantize an AI model, so maybe we grab some model that's already been trained, we get some open source model we want to play around with, make a little chat bot or an internal code assistant, so you can play around with the models where they can link up to GitHub, and you can have things that or so not to GitHub, sorry, to VS Code and code window type applications where that can help you with code autocomplete and things like that. You might want to run your own one, particularly if you're writing some sensitive code that you don't really want to share with GitHub or with any other kind of model provider. You want to run it locally. So you take that kind of model, we say, all right, convert everything just naively to a low precision format. That's one way you can do it. If you don't have the hardware to do the maths in low precision, every time you load a bunch of weights, you just put it back into a format that you can do the calculation, and then back down again, and you can just do it that way. Trade-offs here really, typically the main one is accuracy. If you just say everything right, all these floating point 16 numbers, make them all float 8 or float 4 or something, you might find that you lose some performance. You might find it just can't do the job. You might find a fairly gradual trade-off, and then suddenly, beyond a certain point, it just can't do it. That's where we need to balance this kind of, we get better speed or better power efficiency or something like that, or I can run it on a smaller device, but it's got to actually be accurate enough to do the job that you want. So we said, why do we need to quantize them? Obviously, we know about cases where we've got limited resources. Money is obviously a big one, but it really is getting quite sort of crunch time really with some of the energy cost. These images are done with stable diffusion, and it is quite dystopian, some of them. So data centers aren't quite looking over some kind of end of the world scenario just yet, but hopefully the future's bright with some of the techniques we can use here. So just some sort of stats that we've pulled off the internet. AI, crypto, data centers, that sort of unit of energy usage amounts to about 2% of the global electricity demand in 2022. This is a little while ago. Just AI by 2027 is predicted to use more power than all of the Netherlands put together, which is a break from the usual. Most of these stats, everything, if you see the rainforest being decimated, it's normally the area size of Wales that's always been got rid of. So it's nice that it's the size of the Netherlands this time. It's a little bit bigger. Looking at things like we said earlier, the amount of flops you need for training versus inference. Typically training's got twice as many things going on. In 2022, Google reported that 60% of their machine learning power usage was inference, so more than the training, which shows we're getting to a point where we're not just experimenting with training models, we're now seeing a lot of power usage because we're then deploying them to things like Gemini, or you do a Google search and you get some of the AI power results. Things like Claude from Anthropic and ChatGPT are similar. They're training a model once, that's a lot of energy, a lot of money, but you're then deploying it for a lot of people to use. It's running 24/7 all across these devices, so that power's adding up as well. So even just the inference part, it's not just training that we want to make efficient, it's later on as well when we're running inference and running these sort of services. Unsurprisingly, generative tasks use a lot more power. If you've got a model that can tell you whether it's a cat or a dog, that's not all that powerful really. If you've got something that can write a whole essay for you, or As we had a silly internal challenge yesterday, we did with a bit of a group get together. We got Claude and ChatGPT to write poems about Graphcore. That was quite fun. Probably not the most efficient use of energy in the world, but it's pretty good fun. So anything like that, and particularly things like images, and we're getting towards video as well. Things like Sora from OpenAI. That's really, we're getting some real power-hungry stuff there as well. So on that note, generating an image, obviously it depends on how big an image and that sort of thing, but from a paper found a while ago, it can take as much power as charging a smartphone half the way up. So that's quite a huge amount of power draw there as well. Really weird stat on the side that I wouldn't have thought of until I looked into this, water consumption. So one of the ways that data centers cool stuff down is literally using water. So you have you vaporize water via a heat exchanger, so when the fresh air comes in, it gets cooled down. That's what you then pass over the radiators for all the cooling systems. But you're literally vaporizing the water, all that steam's going off somewhere. So apparently it's something like between 5 and 50 prompts, because it's obviously a huge variation. As if you or I want to chat GPT for a certain task, we might have a big long conversation with it for a big project, or we might just ask it something quick. So huge variation in that, but the average kind of conversation tends to use a 500 ml bottle of water, essentially. That's quite a lot. So some weird amounts of other resources being consumed there as well. And then just a note, it's a lot of text. LLMs, large language models, are getting very large. It makes sense, that's what the first L's for. Everything we do costs energy. So we load some data from memory. This might be the weights of our next layer to do some computation. That's energy. You've got to get it from the memory to register. You store the data when you're doing, for example, a training run. You're then updating these weights, sending them back to memory. All these things cost an awful lot of energy. And this is where we're saying that if you can't go any faster with the loading and storing the memory, you might not be able to get your processor running, doing the maths as fast as it possibly can. So you might find you can't get these theoretical flops that the manufacturer tells you about unless you adapt your algorithm slightly. So we get on to really, and this is the question that was alluding to the question that was asked a moment ago, how much precision do we really need for AI? Because when you think of doing a lot of very maths-heavy kind of simulation things, I've done sort of simulations in a past life as a particle physicist where it wasn't sustainable in float 32. The answers were wrong. You had to use float 64. That's good when every number you're considering is some kind of sort of reasonable, you can imagine what it means. It's a tangible kind of quantity. It has some scientific meaning. The weights in an AI model and the activation, things like that, they don't typically tend to be, if you chopped a model in half and you just looked at the numbers that are coming out the first half of the model, it shouldn't make sense to any of us, really. It shouldn't be something that we can look at and consider like a bunch of English coming out the end of the model. It's kind of, they're very much hyperparameters in the sense of, well, what even are they? So we don't necessarily have the same kind of scientific meaning to them because we can't look at it and go, why is that not a 7? It doesn't make any sense to us in that sense. So all our preconceptions are kind of out the window a little bit there. And what we often find is we have a lot of these parameters in the model. You can often get away with very low precision by having a lot of them. You don't necessarily need to have huge precision like you might expect if you're doing old school simulation stuff. At that point, if you can get away with, say, float 8, why waste all that energy doing float 64? It just doesn't make a lot of sense. And then particularly if you what we call edge hardware, so hardware sort of in your pocket on your phone or on your doorbell, things where you've got battery power, you've got very, very low power requirements. You can't have something taking, even 1 or 2 watts is high in that sense. You want sort of less than a watt for a doorbell, otherwise the battery won't last more than 5 minutes. At that point, then you really want to make sure you're not doing anything more than you absolutely have to. So we'll have a look at how you can do some of this quantization, use lower bits without everything going wrong. So there's a few ways that we can what we call quantize our models such that they still work. So the first one, simplest way, what we call direct cast inference. You take the model, every number that's float 16, or every number that you're interested in that's float 16 or 32 or whatever it is, you just make it float 4 or float 6 or float 8, and then just try it. See how you go. As simple as you can. Depending on your hardware, it can either do the maths with those precision, or you just send it back up to something you can use when you do the maths, but for storage you keep it quite low. And then we get onto some cleverer methods. You might find that works to a certain point and then sort of drops off. So can we kind of, without going right back to the drawing board, blank canvas, can we make things a bit better with a model we've got in a higher precision, but it's too big, it's too powerful, or it's just unnecessarily hungry for what we want to use it for? Can we improve it such that when we then make all the numbers less precise, we get away with it? So I've got a few things we can go into here. One of them is what we call post-training quantization. So we're not feeding all the data back into the model again and retraining it. Maybe we use a little bit for calibration, but typically what we're doing here is trying to say, well, from this layer, what comes out of that layer and goes into the next one, let's make it so that when we quantize the values, it doesn't change that much. So then we can try and calibrate it that way. And then we can do things like we call error diffusion. So you don't just look at this layer into its neighbor, you look at what's the propagation all the way up to that point, such that you can try and recalibrate. And then we have what we call quantization aware training. So at this point, maybe we're not doing all the training, maybe we're just doing the fine tuning at the end. So it generally gets the idea of a language, but it doesn't know what the task is yet. When we're training it on that final task, so your job is to score essays out of 10, or your job is to write me an email that doesn't sound too snarky or something like that. During that process, we take into account the fact that we're going to be quantizing these models. We add an extra term maybe into the loss function. So when it's doing all this, how much did this layer contribute to the model being wrong? It takes into account that when we run it in the real world, we're also going to lower the precision of these values. And then during the back propagation, when we update the weights in the model, we can kind of take that into account a little bit and just train it slightly differently so that it should be more robust. Another thing we can do for the memory usage story, this is slightly out of sync, I think this slide actually, but never mind. One thing we can do when we're using these kind of lower precision formats is you want to make sure that you can actually store things sort of nice and efficiently packed in. Like a tin of sardines, you don't want gaps, you want everything to be sardine. Imagine if you had a weird restaurant. You've made a restaurant, but you've made a mistake, and for some reason, all your tables have 8 seats, regardless. Computers like 8. 8's a nice number to load things in. You want to load 8 bits or a multiple of 8 at any one time. Wouldn't it be great if 2 groups of 4 came along and they could use the same table? Perfect, you haven't got 4 empty seats. That's what you kind of want to do. So what we can do when we're using sort of float 4, for example, if you just store a float 4 on a computer, you'll probably actually find that it's a container that can take 8 with 4 seats full and 4 seats empty. So that's not very efficient. So in terms of the bandwidth and the storage, we actually get no benefit at all over float 8 if we're not careful. Well, what we can do with this, I've got a whole load of float 4s here, and these coloured bits here show the bits that are actually doing something. The white bits at the front, they're just empty. We don't do anything with those, we ignore them. So if we just take half of these, the green half, and we just shift them to the left by 4 bits, or to you, that's left, then we can stick them all together. So then we only need half the memory now, but without doing these kind of clever tricks, then we might find that we don't just automatically get the benefit, because if our hardware is not aware of what we're trying to do, we might find that not everything sort of falls into place. 6 is weird, like I say. So that's what we've been working on. One of the things we've been working on recently is packing 6 into 8. So imagine if, again, this restaurant with tables of 8, now you have to start chopping groups up, because if a load of groups of 6 come along, you might find that, well, 4 of them can go there, 4 of them over there, 4 over there, and then 2s. But with a bit of fiddling, we find that we can store 4 lots of 6 in 3 lots of 8, and that seems to work pretty well. All right, so I'm going to quickly whistle through. There's some novel new types of data for AI where we can bridge the gap between low precision, less accurate. Is it maybe not accurate enough for our purposes, and the higher precision, but it's very power hungry. So one thing people are looking into is some what we call group scaling formats. So you go to super low precision, like float 4, but per block of these, maybe per block of 32 of them or something like that, you apply a scale factor. So then, a bit like going back to the exponent and the mantissa of the floating point formats, if we've got a load of really, really low precision numbers here, to help bridge the gap of how big a range they can cover, obviously very coarsely because they're low precision, so you haven't got a lot of values in between other values, this scale, some exponential value, can multiply by that so that you end up with a much better range. So you can have sort of small variation between these values, and then this can be huge, it can be tiny, so the next block of say 32 might be quite different entirely. So you just, at a coarse level, you can bridge that gap. And this is similar, so this is a sort of fairly standardized format that we're looking into, but again, going back to the DeepSeek work, they did their own as with a lot of these things, they did it their own way, and they looked at a really, really coarse way of doing it. They weren't doing float 4, they were doing float 8, but rather than doing a line of, say, 32 of these, they were doing a 2D block of 128 by 128, so a lot of numbers. Actually not entirely unsensible to do 2D, because one of the things you do when you do a backward pass is you transpose it, and if you've got a 2D block with one scale factor, the scale factor applies whichever way around it is, so that's quite efficient. So this helps us bridge that little gap and allows us to kind of keep the efficiency but retain a bit more of the accuracy. And as you see in a random benchmark that I ran a while ago, typically the performance is quite good. This is one of many challenges you can run. There's lots of benchmarks online that are all cooked. But at the bottom in the blue, we've got the Float 32 performance in terms of accuracy on some Q&A type challenge. There's also things like a computer science exam it can run and this sort of thing. Going to 8, 6 and 4-bit with the scale factors, it's pretty close. On its own, it's kind of meaningless, but generally speaking, we retain quite a lot of the performance, because even though there's hardly any data in this format compared to this, the ensemble of all those parameters trained together gives us the overall ability to do the job that we want it to. And the last thing I want to whistle through very, very quickly, because I know we're all starving, is can we quantize non-LLMs? We're talking about LLMs all day today, really. DeepSeek, a lot of that work is all large language model focused. One thing that's interesting is, what about other kinds of models? So we have a little bit of this in the doorbell that can recognize the person with the parcel, but that's all kind of very much one application specific. What if we just take some other model, maybe Stable Diffusion, image generation, and I start then lowering that model into lower and lower precision. So I asked Stable Diffusion, I forget the exact prompt, but it was something along the lines of a sports car driving through the rolling hills of Tuscany, drawn in the style of Tintin. And that's what it gave me. It got a bit carried away with Tintin. It's almost spelt Tintin on the number plate. But you can see it's quite nice, you know, there's no one actually in it, but hey-ho. Maybe they're taking the photo. We've got nice rolling hills here, quite a bit of detail. There's a little chateau over there. That's quite cool. I ran it with the same prompt, the same random number seed. Everything was identical, except I took the main bit of the model, not the bit that takes text into instruction, not the bit that sort of checks it over afterwards, the main meat of the model, the UNet, and I said, okay, do it again, but this time, float 8 with my group scale format. And I got this. It's almost there. Pretty similar. We've lost the chateau. That's gone. But we've still got a fair bit of detail here. The sunset's nice. For some reason, we've got a heart. I don't know. No idea where that's come. It's a diffusion model, so its job is to take random noise and make an image. So the idea of where did that come from isn't really a question you can answer sometimes. Float 6. Less detail, but actually it's kind of got away with it because it hasn't drawn the sun wrong. It just hasn't drawn it. So in some ways, we've got away with it. We've almost got the chateau back, but it's burnt to the ground. But Tintin's back on the number plate, so you know you get a bit plus or minus. The weird thing is, and it's not always the case with every image that it's the same point that it drops off, but going to float 4, it's like someone else drew it. It's the same kind of image, it fits the same description, but it's like a different artist did it. And that's the point where things fall off in a way that you don't always expect. So that was just not really scientific, it's just a one-off example. Oh, the car's also flying, that was quite interesting. But just to explore kind of a visual example of how this sort of thing works, I thought it was quite fun. Just to wrap up, the last sort of thing to say is, first of all, thank you, but also that we're hiring. So if you're interested in a job, have a word. Thank you very much.